So let's look at series and parallel circuits then. And the first thing for us to look at is the basics of circuits. So let's start by considering the basic variables. So we have potential difference, and that is the work done per unit charge, that is to say per coulomb, between 2 points in the circuit. So it's work, and work of course is energy, and so it's measured in joules. And charge, well, that's measured in coulombs. That's a lowercase c, by the way. So, potential difference, units, volts, symbol capital V. It's also joules per coulomb. So 1 volt means that 1 joule of work is done in moving 1 coulomb between 2 points in the circuit, say between here and here. If this was a 12 volt battery, then moving 1 coulomb from here to here would be 12 joules of work. So that's potential difference. Let's consider current then. Well, that is the rate of flow of charge. So rate of flow, that means it's got something to do with time, right? So that is per second. You would talk about the rate of loss of water from a bucket in milliliters per second, the rate of flow of water through a pipe in liters per second or meters cubed per second. And charge, of course, again, is in coulombs. So current, we all know, is measured in amperes, which we usually shorten to amps, capital symbol, sorry, the symbol capital A. It's also coulombs per second. So we have potential difference and we have current. One more thing to think about here in terms of quantities, and that is resistance. Resistance, well, that's a little harder to define in nice scientific terms. Resistance was a term coined by Mr. Ohm when he came up with his law, which said that the current through a device is proportional to the PD across it, as long as you don't change anything like the length of it, the cross-sectional area of it, the temperature of it. And what he said was that V is some constant times I. V is IR. There's your resistance, right? So really, R is, resistance is the ratio of the PD across a component to the current through it. It's measured in ohms, and that's a lowercase ohms symbol, omega. So, those are our quantities. Let's now think about some real fundamentals. There are two laws that always apply. One is the conservation of energy. There's a thing you've come across a lot. You can't make it, you can't destroy it, you just move it from one store to another, change it from one form to another, but the total amount of energy remains the same. So, in terms of a circuit, if 12 joules of work is done in moving my Coulomb from here to here, then 12 joules of work must be done going around the circuit to get back to here. If we think about this electrical work being done like a hill, you know from previous work, here's our ground level. If we climb the hill, we gain mgh joules of gravitational potential energy in doing that. And if you come back down the hill again, you lose that mgh. So, in the same sense as if you go from here to here and let's say my 1 Coulomb gains 12 joules of energy, then when it comes back around the circuit again, I haven't got a circuit at the minute, but if we had a circuit, when it gets back to where it started here, it has to lose those 12 joules again. Because we're back where we started and we can't be any different to where we started. So gain 12, lose 12, gain 12, lose 12. Now, that's an absolutely fundamental law of physics. That has to happen. If you think about it, you could go from here, at the bottom of your hill, to here, directly, or you could go from here, in the middle of the town you live in, and you could go via China, and then get to the top of the hill. Your change from where you started to where you finished is still mgh. And so in our circuit, it doesn't matter what path we take to get from here to here. Whether we had 4 different paths to get us, I just sketch a few things in here quickly. If we had 4 different paths, I've missed a path here, hang on, sorry. Since I said 4. If we had 4 different paths going from here to here, you would still drop your 12 joules for every Coulomb. That's a really important point. We'll come back and explore that a little later. The other conservation law is the conservation of charge. Now, you might not have come across this one, but it kind of makes sense when you think about it. And the conservation of charge that says, if I take a point in my circuit, let me just make this into a circuit for now. and I needed a component in there, so let's get rid of a bit of the wire, and I'll stick a component in there, resistor. Okay, so make that into a circuit. So we have current flowing into this point. Let's say we have a current of 3 amps flowing into this point. Now, if that 3 coulombs per second comes into this point, it has to come back out again. There's nowhere else for it to go. So if I've got 3 coulombs entering this point every second, I must have 3 coulombs leaving it. Same applies here. If I've got 3 coulombs going in here, I have to have 3 coulombs coming out. And in fact, if I have 3 amps here, I've got 3 amps absolutely everywhere in this circuit. If I had a second branch in my circuit, then some of the current will go this way, some of the current will go that way. So let's call that one I1, call that one I2. But if I had 3 amps going in here, I have to have 3 amps coming out of here. So I1 plus I2, those two have to add together to give me 3. Now, of course, how much of the current goes this way depends on how difficult this path is compared to that one. If this is really easy, then more of the current will go this way. If it's really hard, then more of the current will go the other way. So let's say we had 2 ohms and 2 ohms. Well, they're equally difficult or equally easy, so I1 and I2 are going to be exactly the same, 1.5 amps. If, however, this was to be, oh, didn't mean to do that. If this was 4 ohms, for example, well, this is twice as difficult as that. So half the current that's going through here will go through here, because this is twice as difficult. So you're going to have I2 will be 2 amps and I1 will be 1 amp. Because I2 is twice as easy, and so you'll have twice the current. Bearing in mind that what I've said is whatever this is, whatever that PD is, will be the same between here and here, which means you have the same PD across the 4 ohm as you have the 2. Remember the conservation of energy. V joules per coulomb gained, V joules per coulomb lost. Doesn't matter whether you go through the 4 or the 2, you're still going to lose V joules per coulomb. That's how it works. So, we have talked about what we mean by current. We have talked about what we mean by potential difference. We have talked about what we mean by resistance. Now let's look at some figures. Let's say we have 12 volts. And let's say we have 4 ohms. So, by Ohm's law, V equals I times R. I is V divided by R. Our current is 12 divided by 4. It's 3 amps. Okay, so we've got 3 amps flowing in our circuit. what would happen if rather than having 12 and 4, we had 12 volts and 2 4s? Well, now, of course, all of this behaves like it's 8 ohms. So now we have the current is 12 over 4 plus 4. 12 over 8. 3 over 2. 1.5 amps. So previously we had 3 amps. Now we've got 1.5, double the resistance. So that's 1.5 ohms, right, 1.5 amps. Let's look at three resistors in series in more detail. So, let's say that we have the same as we had before. I'm not going to put the ohms on here just to save cluttering things up. So we have 3 resistors in series, and our current will be, as it was before, V divided by R, which is 12 divided by 4 plus 4 plus 4. So now we have 12 over 12. That gives us 1 amp. So when we had 1, we had 12 divided by 4, gave us 3 amps. When we had 2, we had 12 divided by 8, which was 3 over 2, 1.5 amps. And when we had 3, we had 1 amp. So there we have 3 resistors in series, 3 times the resistance of 1. 2 resistors, twice the resistance of 1, and therefore half the current. So that's resistors or components in series. The current through each of these is the same. Clearly, if I have different values of resistor, if these were 8s rather than 4s, then the current would be smaller, but whatever current flows into this one flows out of this one and into this one, out of this one, into this one, and so on. The current is the same. In your series circuit, the current is the same everywhere. And the PD here, the PD here, the PD here, they all add together to give you the PD here. So these being 4 ohms each, they're the same. Each will have 1/3 of the PD, which happens to be 4 volts. Just if we made those 8 ohms each would still have 4 volts, just in case there's any confusion that the PD goes with the resistance. It doesn't in that sense. The values are not the same, but if the resistors are the same value, then the PD across them will be the same. So that's resistors in series. Let's look at resistors in parallel then. So here I've got 2 resistors in parallel. Let's again say we've got 12 volts. It's a nice handy number divisible by lots of different numbers. And let's again say we've got two 4-ohm resistors. So, like we said before, current comes here, some of it goes that way, some of it goes that way, but the total remains the same. Now, comparing this to having just a 4-ohm resistor in the circuit, we now have two 4-ohm paths. So more current can flow now than we had if we had just the single 4-ohm resistor. Because we haven't just got one, but we've got two. So we have doubled the number of paths of this difficulty, so the current out here will be twice as big. So, to round this up then, let's look at three resistors in parallel. And let's look at again, we'll say we've got 12 volts and we'll say we've got 4 ohms, 5 ohms and 6 ohms. And I'm doing that because there's an important point to get here about the PD across these. Now remember we said 12 joules per coulomb gained going this way. Previously I had the arrow up there, but it's the same idea. And therefore, however we get from this point back to this point, we're going to drop out 12 volts. So going this way, just avoid my 4, or going this way around the circuit, or going this way around the circuit, we're going to drop 12 volts whichever way we go. So, like we had in the previous one with just two resistors in parallel, the PD across each of these is the same. Doesn't matter their size, whether this is 4 ohms or 4 million ohms, the PD between the ends is the same as the PD between the ends of the 5 ohm resistor attached to it. So, the PD is the same across all components in parallel with each other. But of course the current, I just undo some of these so we can see what we've got. The current, previously we had two 4 ohm resistors in parallel, and we said that, well, because we had two 4 ohms in parallel rather than simply one in series, the current was twice as big. Now here we've got a 4, a 5 and a 6. Now if we started with just the 4 and we didn't have the 5 or the 6, then it would be like our first circuit, our 4 in series with the 12 volt supply, and we would have the 3 amps. But if we put, let's say, the 6 in there, now we have a second path in addition to the 4 ohm path that we had before, and so more current will now flow out here because some is flowing through the 6 that wasn't flowing before. You've still got 12 volts across the 4 ohm resistor, you've still got your 3 amps flowing in there, and you've got 12 volts across a 6 ohm resistor, so you're going to have 2 amps flowing in there, aren't you? If you think V equals IR. I've got 12 volts across it, I want the current, I've got 6 ohms. So it's 12 divided by 6, it's 2 amps. The 5 ohms, that's a little bit harder. If I thought about it, it would have picked a different number, but I've got 12 volts. So 12 divided by 5 would be 2.4 amps. So that, can't draw it in there very easily, 2.4 amps. So if I had just the 4 in series, I would have had 3 amps, like we had before in our first example. If I have the 4 and the 6, in parallel, I've got another 2 amps. So now my current here is 3 plus 2 is 5 amps. And if I then added in my 5, which I should have taken the strike out of, but we'll pretend I did that. So if I add in my 5, I've now got another 2.4 amps. So I've got 2, 4.4, 7.4 amps flowing out there. So in our series circuit, the current everywhere in the series circuit is the same. I've got 7.4 amps running out here, and I've got 7.4 amps flowing out of this parallel arrangement and back to the power supply. But in the middle here, in my parallel bit, all the currents add together to give me the current out here. In my series circuit, the PD across my resistors in series, if we look at our 3 resistors in series again, the PD across this one, plus this one, plus this one gives me the PD across the supply. So if they were all the same, each of those would have 1/3 of the supply PD. If we go back to our 3 resistors in parallel, the PD across each of these is the same as the supply PD because I've got nothing else in the circuit apart from what's here. The current that flows out here splits through my parallel circuit, rejoins over here, so the current here and the current here are the same. So let's summarize that then, all of what I have said. Let's summarize that. And let's take away some of this other stuff. So here we have our summary. Series circuit, current is the same everywhere. The sum of the PDs across the components equals the supply PD. And the total resistance, or the equivalent resistance in the circuit, is the sum of the individuals' resistances. If we then look at parallel circuits, here, rather than the current being the same through them all, the PD across all components in parallel with each other is the same, and the current in the main part of the circuit, we'll call it that. The bits either side of the parallel bit is the sum of the currents through the parallel components. Now all of that is a summary of what we have seen as we've gone through the various scenarios.